In this video, I am going to go over glycolysis, and I know it looks crazy and hectic and there's a lot going on right now, but we're going to go step by step focusing on the main pathway of glycolysis. This flow chart here has everything from glycolysis, gluconeogenesis, all the way down to the Cori cycle, Krebs cycle, fatty acid oxidation, glycogen breakdown, insulin. It has everything. So this is a really great flow chart and tool to have, and I highly recommend making one on your own, but I'm going to go step by step kind of explaining how to fill it out, how everything connects to each other. But right now we are just starting with glycolysis, which is this in black. So let's get started. Also, the completed notes from this video will be on my link tree, which is in my bio, or if you're on YouTube, it is in the description as well. This one specifically will be under biochemistry, and then the title will be glycolysis. So, glycolysis. The overall equation of glycolysis is glucose to pyruvate and ATP. So the goal is to turn glucose, one molecule of glucose, into 2-pyruvate and ATP. So start off with glucose. So glucose is a 6-carbon sugar with this kind of format. The first step takes glucose and turns it into glucose 6-phosphate, what we would call step 1. And the enzyme that catalyzes this reaction is called hexokinase. And the reaction itself is a phosphorylation. And this is easy to tell because it goes from glucose to glucose 6-phosphate, which means it just adds on a phosphate group to this 6th carbon right here. And I will draw that out. There is just a phosphate group that is added onto that 6 carbon, and that is the first step. But also what goes along in this first step is the use of 1 ATP. So this is showing that it takes in 1 ATP and turns it into ADP. That's where that phosphate comes from. So as you may notice, we are not producing any ATP yet. This is still the energy investment phase, so it takes ATP to make ATP. Next, from glucose 6-phosphate, we go down and it turns into fructose 6-phosphate, and this is step 2. There are 10 steps. So this reaction is catalyzed by glucose phosphate isomerase. Okay, and this reaction is an isomerization. And so this basically, nothing is being added here, so we don't need any ATP, no phosphates are being added. The arrangement is just going to shift around and change. So this is what fructose 6-phosphate is going to look like. So if you notice, it is now a 5-membered ring instead of a 6-membered ring that we have up here. Everything is still, no atoms were added or removed. It is just a shifting around of the bonds, which is an isomerization. Next, we turn into fructose 1,6 bisphosphate. And so you can kind of tell here already that we are probably going to use an ATP, which we are, because we now have fructose 1,6 bisphosphate. So there's going to be a phosphate on both the first carbon and on the 6th carbon. And so this is catalyzed by an enzyme called phosphofructokinase, or many people just abbreviate it to PFK. And so this step, again, is a phosphorylation because we are adding on that phosphate group. And this is also part of the energy investment phase because we are using ATP. This is the overall what we have right now. So these are the first 3 steps of glycolysis. So far we have glucose to fructose 6-bisphosphate. We've added 2 phosphate groups from 2 different ATPs. So far we've only used 2 ATPs. From here, there's a cleavage. So it's not transforming just into one thing anymore. You're going to get 2 different products. Glyceraldehyde 3-phosphate, and also a molecule called DHAP. And so, the enzyme that catalyzes this reaction, step 4, let's write that. Step 4 is called aldolase. And this is a cleavage because we're taking this 1 fructose 6-phosphate and we're splitting that up into glyceraldehyde 3-phosphate and DHAP. DHAP is then going to go through an additional step to turn it into glyceraldehyde 3-phosphate. So we'll call this step 5, and this is done by an enzyme called triose phosphate isomerase. This is an isomerization reaction, and this is going to get us back to glyceraldehyde 3-phosphate. Okay, great. So now we have 2 molecules of glyceraldehyde 3-phosphate. One just had to go through an extra step to get there. So keep in mind, this is all from 1 molecule of glucose. So we have 1 molecule of glucose going all the way down now to 2 glyceraldehyde 3-phosphates. Let me draw this out. This is what it looks like. Okay, moving on from here. Remember, there's 2 of these. So everything that we do from here on is going to be doubled because we have 2 of these glyceraldehyde 3-phosphates. So now we are entering something called the energy payoff phase. So we finished the energy investment phase. We've invested 2 ATP, and now hopefully it's going to pay off and we're going to get a higher yield of ATP. So glyceraldehyde 3-phosphate gets turned into 1,3-bisphosphoglycerate. Wow, that is a long word. 1,3-bisphosphoglycerate. And so this is step 6. And this is catalyzed by an enzyme called, bear with me here, glyceraldehyde 3-phosphate dehydrogenase. And what also happens in this reaction, step 6, is when we start to add on our oxidation and reduction reactions. So this is going to take 1 NAD and it's going to reduce it and turn it into an NADH. So we would classify this as a oxidation reaction. But if you notice, there's also a phosphate that is being added. But this phosphate does not come from an ATP. So this is also a phosphorylation now that we have 1,3-bisphosphate. Okay. What is important about step 6 that we can note is this is often called the characteristic step. And this is because this is the first time that NAD is getting reduced. So glycolysis is a process that produces NADH. So it's called the characteristic step because that is the step that it is doing it in. So that's just an important thing to remember. Moving on to step 7, we are forming 3-phosphoglycerate. 3-phosphoglycerate. This is step 7, and this is catalyzed by an enzyme called phosphoglycerate kinase. So you might already notice that up here, there is 2 phosphate groups, and down here there's only 1. So you know that we're going to be removing a phosphate. So we can go ahead and classify this as a substrate level phosphorylation. We are giving that phosphate back to ADP to turn it into ATP. So we just made our first ATP. Awesome. It's also important to note that this intermediate is a high energy compound. This is what allows it to give that phosphate up into form ATP. Next, on to step 8. We are almost done. Step 8, we turn this into 2-phosphoglycerate. 2-phosphoglycerate. This is step 8. And this is catalyzed by an enzyme called phosphoglyceromutase. And this is an isomerization reaction. So here, there's no phosphates being added or removed. It just goes from the third carbon to the second carbon. So that is a pretty easy step to remember. Quickly moving on, we form phosphoenol pyruvate, or PEP. This is step 9. This is catalyzed by an enzyme called enolase, a simple one, and this is a dehydration reaction. And that's all that happens here. We just form PEP. And so the very last step, obviously, is going to take us to pyruvate because that is our goal. I'm gonna make this one extra big because we're gonna add stuff on later. This is going all the way to pyruvate. And this is step 10. This is catalyzed by an enzyme called pyruvate kinase. And just by the word kinase, you already know that this is going to be a substrate level phosphorylation. And since it is a kinase, we are going to be taking an ADP, adding a phosphate group, and turning it into ATP. Okay, that was the last step. We got all the way to pyruvate. Let me draw out what pyruvate looks like. It is a 3-carbon molecule. Notice it's the same as when we split up the 6-carbon glucose. We didn't gain or lose any carbons. The only things that we're adding on are the electrons and the phosphate groups. So we got all the way down to pyruvate. And so let's look at our overall scheme that we have here. Glucose comes all the way down, and we invested 2 ATPs here. So 2 ATPs gone. Now, once we get down to our energy payout phase, this starts at kind of step 6, our characteristic step. It goes all the way down, and as you see, we only have 2 ATPs being made. So you might think, well, we just broke even. But you need to remember that we have 2 of these glyceraldehyde 3-phosphates. So everything from here on out, remember, is doubled. So we actually made 4 ATP. But since we spent 2, the total yield of glycolysis was 2 ATP. So we took 1 glucose molecule, we turned it into 2 pyruvates and 2 molecules of ATP. And also 2 molecules of NADH, because it does form NADH as it is an oxidation reaction. So this is our final schematic. This is glycolysis. We will add more on later when we do gluconeogenesis and then Krebs cycle and all of the activators and inhibitors we can add on here too. But pyruvate is kind of our central hub. This is where we're going to start citric acid cycle or anaerobic oxidation and all that, but we will get into that later.